A'udhu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. In today's lecture, we will discuss the optical properties of nanomaterials. This lecture is from the course outline of Nanophysics and Technology course, and the course code for this course is PHY445. Actually, when electromagnetic radiation interact with the matter, so their optical properties are generated. So the optical properties are closely related to the electronic and electrical properties of the semiconductor material, but we will see in the upcoming slides that it not only depends upon the electronic structure, but there are some other factors on which the optical property depend. So when some electromagnetic radiations, a ray from the electromagnetic radiation which is monochromatic, interact with the matter, then there are three possibilities or three different processes will occur. I mean, depending on the wavelength and energy of that upcoming electromagnetic radiation. The first one is the reflection process. In the reflection process, the upcoming rays is reflected in different directions. So the refraction is further divided into two categories. One is specular reflection, another is diffuse reflection, and depending on the nature of wave. And the other is the refraction process or the transmission process. In this case, the rays pass through the material, so this is actually called as the transmission, or the rays is transmitted in this case. And in third case, there is the absorption. There is also possibility that absorption of the ray occur, and in this case the electromagnetic radiation is absorbed in the materials and that is vanished. So this is the simple process of reflection, refractions, and absorption. In general, the interaction of electromagnetic waves with matter is divided into two basic categories. There are two possibilities when the electromagnetic radiation interact with the medium or with the matter. So the first one process is the scattering, and the second one is the absorption. In the case of scattering, the electromagnetic radiations are scattered in different directions, while in case of absorption, the electromagnetic radiations are absorbed and vanishes completely. So if one consider a wider spectrum of frequency, then some part of the spectrum could be absorbed, while other frequency could be scattered. So it depends upon the nature of the radiation as well as the nature of the material. So absorption actually involves activating some process in the material, and that is actually the excitation of material from its ground states. So there are different processes which are possible for this activation of or movement of a system from its ground state to excited state. The first one is that there might be electronic transition. The electron from ground state is moved toward the excited states. If we consider an atom, so in this case the movement of electron between atomic orbital will be responsible for that. If you consider molecules, then in case the electron will move between the molecular orbital. But if we consider a solid, maybe say semiconductor, so in this case the electron is moving from the valence band toward the conduction band, and this causes the absorption of the electromagnetic radiation. The second one process that is responsible for the absorption of electromagnetic radiation is the vibrational transition, and in this case the upcoming electromagnetic radiations are change the vibrational state of the systems. And the third case is the rotational transition, in which the electromagnetic radiations change the rotational transition, the rotational system of the molecules. Atoms, molecules are solids. So as a result, the energy or electromagnetic radiations are absorbed. In some cases, the absorbed energy, definitely when the energy is absorbed, so the atom or the system or the solids or the molecules cannot remain in its excited state for longer time, so the energy must be re-emitted. So in some cases the energy is re-emitted but in some cases the absorbed energy is dissipated in the form of heat, and such absorption is called as dissipative absorption. The energy vanishes, and that is it is converted into heat, other form of energy, that is heat. So it is called as a dissipative absorption. So electromagnetic waves, when it fall in an atom, so what occur, the electron cloud is set into oscillation. So this situation is like a dipole oscillator which emit radiation of the same frequency in all directions. So this is the process of scattering. So similar to absorption, scattering is also a frequency dependent process. So there are two possible ways in which transmission can take place. The first one is that if the medium is sparse, the ray could just pass through the particle of the medium, like we consider in the case of vacuum, which is essentially means there is no interaction. But if we consider more common mechanism for denser media is forward scattering, and what we call as a transmission is coming we call as transmission is common usage as actually forward scattering. So this is the way how we can find out the refractive index of the material, because we can measure the difference between the velocity of the material in the medium and in the vacuum. When a wave or a ray is transmitted from one medium to another medium, so what happens, its frequency remains constant but its velocity decreases, or there is change in the velocity of the ray. So the ratio between the velocity between the medium and in the vacuum is called as the refractive index. So definitely the wave being slower in the medium, so this is actually n is equal to c divided by v, and in this case is equal to epsilon mu naught divided by epsilon naught mu naught under the root. This is actually the value of the refractive index for any particular medium. Here in this case, epsilon is the permittivity of the medium, where mu is the permeability of the medium. The subscript 0 refers to the values in vacuum. So Ke is the relative permittivity, that is actually the dielectric constant, and Km is the relative permeability of the medium. So usually the Km is close to unity, I mean this value is very close to unity, but the value of K is a function of the frequency of the electromagnetic wave and leads to the phenomena of dispersions. So physically the origin of the dependence of n on frequency is due to the following factors. The first one is the orientational polarization, we will see in the next slide. The second one is the electronic polarization, that will be also discussed in the next slide. Ionic polarization and the space charge. So here we can see the electronic polarization in the first part of the figure. So in this case, when there is a neutral atom, the center of the positive charge and the center of negative charge are at the same point. But when an external electric field is applied, what happens? The center of the negative charge is shifted in some direction due to the electric field from the center of the positive charge. So there is a type of dipole. A dipole moment is created. I mean the center of positive charge is located at some distance from the center of negative charge. So this creates a dipole moment, just like P is equal to Q D, where Q is the charge and and D is the distance between the center of positive charge and the center of negative charge. What we discussed in ionic polarization is that the ions which are regularly present initially, when some external electric field is applied on it, would happen, it rearrange, but the arrangement is in such a way so that the bond length between the atoms changes. So it moves the center of positive charge from one point toward the center of negative charge from one point toward the center of and the center of positive charge at the other point. So they are located at some distance to each other, creating the polarization process. The other is the orientational polarization. The atoms which are arranged in different structure and in particular degree and particular angles would happen when external electric fields are applied. The molecules are rearranged or reoriented. So this reorientation causes migrate the center of negative charge from the center of positive charge, leading to a polarization process. And the fourth one is the space charge polarization, in which the charges are randomly present and a regular pattern initially, but when some external electric field is applied, so the charges are separated from each other, creating the space charge polarization. So usually the refractive index or the value of n is greater than 1, that is equal to n is greater than 1, but under certain circumstances it can be less than 1, for very special cases or even be negative. So what is the physical meaning of negative refractions? When n is less than 1, it implies that light is traveling faster than speed of light, which is apparent contradiction to the theory of relativity. Definitely is contradiction to the theory of relativity is not possible. So what happen in case when n is less than 1, the velocity which one needs to consider instead of the phase velocity is the group velocity, that is called as a Vg, or in still other cases the signal velocity which will be less than c. And in negative refractive index materials are typically structured, the refracted beams will be on the other side of the normal. So the special kind of scattering of importance to material science and diffractions. Actually, we know there is some condition for the diffraction process, and the diffraction process says that there should be some relationship or maybe some of the order of between the diffraction grating, or that is called as the slit, and the wavelength of upcoming radiations. So what happen normally would happen if there is a reflection process, then the wavelength of the upcoming radiation should be very greater than the slit, the A, that is the separation between the atoms. In this case the reflection occur. So the diffraction occur when the wavelength of upcoming radiation is of the order of the distance between the atom, or the slit, the size of the slit. And transmission only occur when the upcoming radiation is very less than the wavelength of the upcoming radiation wavelength is very less than the slit, or the size of the slit, or is even called as the material opening. So through our discussion here we can consider the electromagnetic waves of the scattering and diffractions. That's true for all kind of waves. Young double slit experiment performed in a ripple tank with water as a medium is a good example of the scattering and interference. But in that case we have not used electromagnetic radiation, that was a normal radiation. But we can have make some comparability between them, that how this diffraction, reflection and transmission occur, and what are the basic conditions for that. So how the color originate from the material. So there are different mechanisms that are responsible for that. The first one is the absorption emission process. The light is absorbed, and that is why we can see something and it have different colors, or maybe the emission process also responsible for that. The second one is the reflection and transmission process. The light is reflected or transmitted, that also cause the origin of color. In some cases we have scattering phenomena, just like in the sky, where it looks like looks blue, so that is because of the scattering. This color is originated due to the scattering. And the third one is the dispersion process. The fourth one is the dispersion process, just like the white light that is passing through the prism, and that is the wavelength are shifted, and the white light is converted into 7 different colors. So in some cases we have interference that also originate the color, and in case of interference, the example of interference is oil films or water, or seed or butterfly wings. So here what happens, the upcoming radiation wavelength should be equal to, or the energy of the upcoming radiation should be equal to the difference between the energy levels, and accordingly different lights or different light with different wavelengths will be originated. Here we can see the migration or the transition of electron between 3s and 3p orbitals. So within 3p there are subshells, so the different subshell transition between the 3p and 3s will originate different light, absorb or emit different light. In first case is 589.6 nanometer, while in second case is 589.1 nanometer. So when the electromagnetic interaction radiation interact with metals and it is absorbed in matter, what happens? That is actually plasmas are created, and plasmas are collective oscillation of free electrons. So the bulk plasma are longitudinal oscillation of electrons gaze with respect to the ion cores. So the incoming visible electromagnetic radiation set of plasma oscillations and his is absorbed, that is the bulk metals are opaque in the visible region. So optical property of semiconductors, how it is originated. Ionic crystals show strong absorption in reflection in the IR regions, the infrared region, so due to the interaction of light with optical photons. So compared to compounds of semiconductors that are GaS and GaP have a partial ionic character to their bonds and exhibit absorption and reflection in the IR region. So what is the absorption age for the different energy or for the different electromagnetic radiation that are coming and are absorbed or transmitted? The absorption age is actually the relationship between the wavelength or energy of the upcoming radiation and the band gap. If the energy is greater than the band gap, it will absorb, and the absorption age is equal to V naught is equal to Eg divided by H, that is the absorption age. So the wave vector of a photon in the optical region is very small, and that is only constant momentum transfer allowed across the band gap. So vertical transition case space are allowed. So here we can see on the right side of the figure we can see different type of band structure. The first one is the direct band gap. The definition for the direct band gap is that when the top of the valence band and the bottom of the conduction band lies at the same value of K, then we can say this is direct band gap semiconductor. But in some is not often for all semiconductor, but in some cases the top of the valence band and the bottom of the conduction band lies at different values of K. So that is called as indirect band gap. So there are different conditions for that. There in some case, the transition of electrons in direct band gap semiconductor are simple, but in case of indirect band gap, the transition are a bit complicated. There are some allowed and forbidden transition which we need to know. So in indirect band gap semiconductor, both photon and phonon needs to be absorbed. So the phonon energy is around 0.05 electron volt. That can be ignored, but still we need to take into account. So that is contributing only to the momentum of electron. So exciton is a bound. What are exciton? Exciton are actually the bound state of electron and hole. So the binding is due to the electrostatic attraction, that is the Coulomb attraction. The exciton has lower energy than the unbound electron plus hole. So this brings the energy levels closer to the conduction band and the Bohr radius increases. It is an electrically neutral quasi-particle that exists in insulator and semiconductors. So the exciton can be considered as an electromagnetic excitation in material which can transport energy without transporting electrical charge. That is, the excited state can travel through lattice without transfer of charge. So here we can find out the effective or reduced mass of the exciton, that is equal to Me Mh divided by Me plus Mh, where Me and Mh are the masses of electron and hole respectively. So the photon absorption by semiconductor can lead to the formation of exciton. So this exciton binding energy for most semiconductor is in the range of few tens of milli electron volts. So that is equal to, in this case we have given the value for some semiconductor, and this is at room temperatures have this value. So given the small value of Ex, an exciton can be dissipated by thermal energy at room temperature. So the exciton spectrum has a sharp line just below the fundamental edge. So it is usually absorbed at low temperature where thermal energy is lower than the binding energy. Here in the figure we can see how the exciton move. How exciton is created and what energy is responsible for that, and the energy of exciton is also mentioned in the equation. So here there is a curve between the the curve of the excitonic absorption in different materials, especially in GE. So this is something about the optical property of the semiconductor. I hope we can have some relevant topic, a relationship between the optical and electronic property of the semiconductor in next lecture. Thank you very much.